All right, everybody. Welcome to Thursday night pre-calculus. It does look like I am in a helicopter or a pilot on some sort of air flight or something. But what I'm actually doing is watching my kid play soccer, and I'm actually in the truck cab sitting here watching my boy play a little bit of soccer. So tonight we are going to be doing a little bit of test preparation, looking at some technology tips for students on the AP Pre-Calculus exam. I have with me once again, I've got Steve Kokoska and Vicky Carter, and Tom Dick joined us about 2 seconds before we went live, and I'm really excited to have him on here as well tonight. So I'm going to turn it over to you, Steve, and we will get things started.
All right. Thank you very much, Curtis. Great to be with you and Tom and Vicky again. I think we've got some great technology active AP pre-calculus type problems tonight. I'm going to talk a little bit about these problems to begin one at a time here. I'm going to show some technology screen illustrations from the TI-Nspire. And I'm going to try to talk a little bit about some of the concepts going on behind the scenes, some things to think about. I hope that you've done your homework, Curtis. This is your last opportunity for a passing grade. So I hope that we can ask you some questions and get some good responses. You may have to rely upon some participants, but we'll ask you some good questions anyway.
Well, when my son joins me here in the car, I'll ask him a couple of your questions.
Okay.
How's that?
All right. Well, here we go. Let's try number one. This one's based on some actual data that I found. It turns out that at any given time during the day, there are about between 8,000 and 13,000 commercial airplanes in the air. It's actually true. And on a certain day, let's suppose that this table shows the number of planes in the air, which we'll denote by the variable capital N, and that'll be in thousands, at selected times, T hours since 6 a.m. So there's a table of what I guess 6 values. And the first thing we're going to do here is to construct a scatter plot of the number of planes in the air versus time. And let's describe any pattern that we might see. So this is really very easy and I think intuitive to do on the TI-Nspire. I can go directly into a lists and spreadsheet page. And I put all the values of T in this first column here. Let's see, oops, is my pen working? Whoa, let's try that again. Arrow up here, see if the pen is working. I don't know about that. Well, I get all the hours in this first column over here to the left. I've got the planes, the number of planes in a column, which I labeled called planes.
So, Steve, I think something that's really important and that makes the TI-Nspire so powerful is that you can actually name these columns what they represent, and it makes it a little bit easier to comprehend what's going on.
Yeah, true. Rather than just say X and Y.
Yeah.
Yeah,
Or
absolutely.
L1 and even with the
L1 and
A4,
L2.
it's nice, but it's L1 and L2, and you have to remember which is which.
Yep, good point. Yep, good point. So I chose those. I actually named those columns hours and planes. And then I can go directly to another page on the TI-Nspire, and it's very easy to just create a scatter plot and pick the variable, pick the name of the column that we want on the horizontal axis and the name that we want the data on the vertical axis. And here's my scatter plot over here on the right-hand side. So it sure looks like that those data points follow kind of a quadratic function. That seems to be a reasonable sort of regression to think about. Before I do that, here's a question, Curtis, that you can think about. Maybe the participants can answer. You know, that certainly looks like we can fit a quadratic function through those points. But if I didn't look at those points, if I didn't do a scatter plot, I might blindly just try to fit a straight line. And if I tried to fit a straight line through those points, I wonder what it would look like. But maybe that's something that Tom can try later on, but I wonder what it would look like. Let's look at B. So let's consider an appropriate regression model, and our appropriate regression model is going to be a quadratic model, and I just wrote it like that. N is equal to AT squared plus BT plus C. And of course, what we want to do is try to be able to find those constants A, B, and C. This again is very easy on the TI-Nspire. I can, from that graph screen, ask the calculator to find that quadratic regression equation, and there it is. You can see that it's printed on the screen. And I've even drawn in that curve. And you know what? It's pretty darn close to those points. It looks like it's a pretty good fit. Now, a couple of little things here. If you look at this calculator screen down on the bottom left-hand side, it turns out that on the Nspire, these three constants, A, B, and C, are stored in variables in the TI-Nspire. The TI-84 does this also, stores these constants in variables in the background. The Nspire does that also. A couple of little things here. I have printed all of those on the screen, on a calculator screen, just so you could see them a little bit more explicitly. But I printed them with 3 digits to the right of the decimal. But remember that they are stored much more accurately by the calculator. On the right-hand side at the bottom, I printed a screen of the statistical results from this quadratic regression. I'm not sure, Vicki, help me a little bit here. I'm not sure how much of this that we get into in AP Pre-Calculus, probably not much. But down towards the bottom here, you can see there's a value of r squared. The squared is kind of small there, but that's a value of r squared. That is an indication of how good a fit that model is. The closer that is to 1, the better the fit. And that's about what, 0.89, 889 there. Boy, that's a pretty darn good fit. If I were doing this with real live data that I gathered off of an experiment somewhere, I'd say, wait a minute here, somebody probably made up the data. That's pretty darn good. That's
We
really
do not actually look at the R-squared value in AP Pre-Calculus, but I think
okay.
it's good for students to just kind of have that as some background knowledge, especially if they end up moving on to AP Statistics or even a statistics course in college, because it will
Absolutely.
definitely be discussed there. So just kind of giving them a little more information than they actually need to use.
Yeah. Down at the bottom too, Vicky, help me with this, but down at the bottom too, you can see there's sort of a notation for the residuals.
Mm-hmm.
And that is something that we deal with in AP Pre-Calculus. We're going to take a peek at those in a minute. So all of the residuals are automatically stored, calculated, pardon me, and stored in the
Yes.
background. Okay.
Oh, and Steve, thanks for showing everybody how to recall those values of A, B, and C. Although they're stored in the equation, it's actually stored as a function when you run that regression. I think if you just wanted to recall one of those values, it's really convenient that you see how that can happen.
Indeed, I think it is. Yeah, I think it is. One of the things that students might be asked to do on the exam, I think, is if they find a regression equation, they may be asked to evaluate that equation at a particular value. And so there are many different ways to do that on the Nspire, but here is a way. So that regression equation is actually stored in another variable, stat dot regression equation, and I evaluated that at the value 6 because, well, let's see, that was high noon, so that was 6 hours past 6 a.m., and the value to 3 digits to the right of the decimal is 8.194. I'm pretty sure that Tom will show you how to do that on the 84. And I think one last thing down at the bottom on this problem, I constructed a plot, a scatter plot of the residuals. Yeah, there it is. So a standard sort of question here is there any evidence to suggest a violation in the regression assumptions? Well, there are lots of regression assumptions here, but basically what we're looking for, hoping for here, is just sort of this sort of shotgun effect of these residuals. We don't want to see any distinct pattern at all. If there is some sort of pattern in the residuals, that is a signal that, well, you know what? Maybe we don't have the right model. Maybe it should have been a cubic model, or maybe we should have had a sine, a trig function in there, or maybe it should have been linear. And sometimes the pattern in the residuals can reveal to you the part of the model that might be missing. In this one, there are no pattern in the residuals, so that suggests that there is no evidence of a violation in the regression assumptions. Curtis, I don't know if you can see all the color that the TI-Nspire provides, but that's kind of nice and rich. Helps sort of this come to life a little bit, just makes it a little bit easier to interpret, I think. So, Tom, I think I'll turn it over to you for a little bit of technology on the 84.
Sure, Steve. Sounds good.
Okay, there you go. All yours.
All right. I'll share my TI-84, I hope. There, I hope it comes up okay. Are you seeing that all right?
Yes.
Okay, great. Okay, so basically just wanted to kind of run through what this would look like on the 84. So I'm going to go to the stat editor. And I did take the liberty of going ahead and entering this data in lists L1 and L2 right here in the editor. So these are the same values that Steve was looking at just a little while ago. And we're going to want to do a scatter plot like Steve did. So let's see how we would do that on the 84. So I'm going to go to the second shift of the y equals where it says stat plot. And I see plot number 1. Let's go ahead and use that. So let me enter there. Let's just set it up. Okay, so we're going to turn it on. And the plot type that we want to use is a scatter plot. So that would be this first one here. It looks like there was some kind of line plot on before. So let me turn that on. Our lists, X list and Y list, oh, those already look good. L1 and L2, those are exactly what we want. The mark, let me choose a mark a little bit bigger than that little dot there. So I'll choose a little square. And then as a color, let's see, why don't I try, how about blue? There we go. All right, so let me enter that. And so I've got my stat plot set up. And let me go ahead and hit graph. Oh, let's see, what did I do?
I think there might be something in your Y.
The
Y
Y.
one
There
equals,
is.
yeah.
I think there is. Yeah, let me clear that out.
Oh, that's interesting.
Oh, that's a weird graph. Okay, let's try graph again. Oh, there's no points showing up. But you know, a quick way to take care of that is to go to Zoom and go down there to number 9, Zoom stat. What that does is it picks a window that's going to fit all of your data in it for you. Okay. There we go. Now we have something that looks very much like what Steve had.
Pretty cool.
I think, Steve, you suggested we might, one thing I was going to do here before we try regression is if you hit trace, it will actually plot, it will jump from data point to data point. So there's 0, 12.1, and then as I increment, it's just going through the table of values that we have there. Okay.
Tom,
So go ahead.
One question about this trace. So as you trace along these points, how does it trace? Does it trace left to right, or does it trace by the order in which they are in the table or in your list editor?
I believe
it traces by the order they are in your list,
in the list
editor.
So if I had put them in a different
right,
order,
it is not left to right.
It is not left to right. Okay.
Yeah.
It is not left to right. It is what we're actually incrementing when we trace on a scatter plot is the list index value.
Oh,
so
okay.
you start in the X list index value spot of 1, and then you increase 1, 2, 3, whatever, and you go down that X list, and then the corresponding Y list is what's traced out then.
Okay, gotcha.
Okay, let's try a regression now. So I'm going to go back to stat, and we're going to calculate a regression. So I'll arrow over to calculate and look down there. And I think, Steve, you were curious about what might happen if we tried a linear regression here.
Yeah, wonder what would happen
So
there.
let's try number 4 there. So I'll enter that, and it says, okay, what do you want to do a linear regression on? Well, the X list, L1, that looks good. It looks like the Y list I need to change. So let me change that to L2. There we go. And I want to store the regression equation in Y1.
Okay.
So let me
Sounds
go
good.
to y variables and pick up y1 there. And finally, let's calculate and see what happens. Okay, so there's my linear regression. It gives me an A value and a B value.
Mhm.
Wow, that A value, I think in this case, A is the slope.
Yeah,
That's all, looks like it's going to be really close to horizontal because that A value is
absolutely.
close to 0. I wonder what it looks like if we actually try to graph it. Let me go to y equals. There it is. It got
Yep.
stored in y1. So if we graph this, we're going to graph both the line and the scatter plot together. And there we go. Okay,
How about
so it was.
that?
And, with that kind of shape, this is actually not that surprising. The linear regression is going to try to balance out the distances off above and below the line. So we can kind of see that here. But clearly, that's not a very good fit at all. So let's try that again. And let me go back to stat and calculate this time a quadratic regression. Okay, looks good, L1, L2. And let's go ahead and store the regression equation back in Y1 again. So it will overwrite the Y1 we had from the linear regression. Okay,
Gotcha.
there we go. And let's calculate. All right, I think that's looking very close to the values that you got, Steve. I remember you had like a 0.1 for
Yep, very good.
Let me just go to y equals. Yep, there we go. Looks like it's there. And then let's go ahead and hit a graph. Very similar looking graph to what you had there. Okay. Let's see, I think you were wanting to use this model to estimate the number of planes in the air at 12 p.m. That was a little bit tricky because there's a data value that has an X value. Well, your hours, 12 shows up in that table, but this is hours after 6 a.m. So we really want t equals 6. So if I turn on a trace, now I'm on the scatter plot, but if I hit the up arrow, it'll bounce down to the Y1. And look at this, 6 happens to be exactly in the middle of the screen. So that's great. So it just happened to jump right on there. So we got that. And this was in thousands, so we need to really interpret that. That's actually 8,194 approximately. Great.
Very good.
How about residuals?
Yeah.
Well, let's go back to the stat editor. And let's make L3 actually the values from our regression. So what I'll be doing is evaluating Y1 for each of these values in L1. Okay, does that make sense?
Yeah.
So let me pick up Y1 of, and then I'll put in L1. Boom. Okay, so those are the actual predicted values that our regression equation is giving us. And now in the L4, let me just do a calculation of the residual. All right, so yeah, that's a quick question. Is that the actual value minus the predicted value or the other way around?
Yes, it's an AP course.
Yeah.
Actual minus predicted.
Would it be L2 minus L3 or the other way?
Yeah, I said it wrong. Yes, L2 minus L3.
Okay, all right. I'm sorry if I didn't hear you. Okay, so, let me go up to L4.
There you go.
I'll just put L4 is equal to L2 minus L3. Boom, there's our residuals. And we could plot those residuals just like Steve did. We'd be plotting L1 versus L4 to do that. So if we want to see a quick look at that, let's go to our stat plot. I'll go down to plot 2, enter that. Let's see, we'll turn that on. We'll do a scatter plot. And this is going to be L1 versus L4. Okay,
Right.
L4 is what we want, because that's where we actually calculated those residuals. I'll use a plus sign instead of the square. And let me choose a red for residuals.
There.
All right. And let's see, should we do a maybe a stat plot right off the bat? So I'm going to do a zoom stat. And boom, there we've got them. And we've got the residuals down here. If I hadn't plotted both stat plots, we also have our original. These would be expanded quite a bit because it would give us a Y range that used up is big enough just for all these points to fit. But we can see again, there's no real pattern to those residuals.
Yeah, but let's
ahead,
make it a little
Vicky.
more, let's make it more visible. So let's cut off this first stat plot and then
Sure.
do our zoom stat again, just so they can see what
All
a
right,
little better
I'm going
view.
to turn off plot 1
Okay,
and then just do zoom stat again. So
Yep.
plot 2 is still on. There we go. Okay. And this is much more similar to the plot that we saw.
Yeah.
Yep.
And as Steve said, it's just bouncing up and down, kind of a haphazard thing. And the lack of a pattern is actually good news
Good.
for us. It
Yes.
means that there's nothing else going on that suggests we needed it to account for in this model. The quadratic regression seems to be doing a pretty good job.
Hey, Tom.
Yes.
One thing that's kind of handy about this, just like on the Inspire, you actually do have that list of residuals available to you. Once
Okay.
you've run a regression, once you've actually computed a regression output, the 84 calculates those residuals and stores them in a named list called list resid or L resid. And you can access that if you wanted to by pressing second and the list.
Okay.
And list resid is there.
Number 7 there.
Yeah.
Number 7. So that list is automatically calculated for you. So if you wanted to, you could go back and make that scatter plot. Instead of using list 4, you could use list resid. It'd be the same picture as what you calculated, but that list
Excellent
resid
point.
is a handy piece if you're looking to make those residual plots.
So I think
that's
this is-
excellent point, Curtis.
Yeah.
And I'll also admit too that I actually kind of purposely did it in a little bit longer way because I really wanted to stress what those residuals meant, what they mean. Yeah, I'm sorry I interrupted you, Vicky. Go ahead.
No, I was just saying what you just said. Basically, I think it's important for teachers to demonstrate that so that students actually can identify a residual to a process that they've seen and it makes sense. But then once that happens, then they can start using the residual list.
Oh, yeah.
Hmm.
Yeah,
I'm
that
looking at
actual
the-
minus predicted concept, and just remembering that what we're talking about when we say residual, I mean, it's a word that we all use regularly, right? This idea of we have leftovers, residual things, right? The residual effect of something, whatever. It's the leftovers, right? So it's the difference between our actual value and then any predicted value from that. So yeah, it's worth it.
And I'm just looking at these first 2 values in that list. And if I went back to my stat editor, so I'm seeing 0.34 and 0.025. We go back to the stat editor. There they are. Yeah. And these are the ones I actually calculated from scratch in a sense by taking the actual value minus the predicted value. So yes, so that is nice to know, especially if you've done this several times, you can then take that shortcut and get those residuals very quickly.
Right.
Okay. I'm think I'm ready to turn it back over to
Oh, wait,
unless
one
there's
more.
another question.
Wait,
One more
wait,
question.
one more question.
Okay.
I'm sorry, Tom. I
Oh,
apologize.
that's all right.
Can you go back to the home screen just for a minute?
Sure. Let's see. Let me
So
go.
we know that the residuals are in both L4, and we know that they're in that list right there in front of us. Can you use a built-in calculator function just to very quickly sum the values in that list?
Okay.
Oh, the sum of
So
the
that
residuals.
sum up the residuals.
Yeah,
Let's
is there
see.
an
Let me look at.
operation?
We've got some
Sure
list
is.
math here.
Keep
Yeah, is
going.
there something
Uh,
real quick that you can
oh, I
use?
see
Five.
some here.
Okay.
Some. Well, let's go down to number 5. And let's see, my last answer was this residual list. So let me just go ahead and put ants in there. So I'm guessing that should sum up the values in that list.
Oh, isn't that funny?
So what it come out to be?
What kind of an answer is that?
Small.
Very.
Small.
Very.
That's
Yeah.
very interesting. I wonder if that's always the case. That the sum of the residuals is really darn close to 0, isn't it?
Yeah. I think by
Huh. Okay. Well,
Huh.
we'll leave that as an open
I think
question.
there's a good point there being made. All right.
All right. Very
Stop the
good.
share there and let's
Okay.
turn it back over to you, Steve.
All right. Thanks, Tom. That was great. Very good. Okay. This question concerns the flight of a drone. And this is kind of appropriate because a couple of weeks ago we were in Dallas for the T-Cube conference. And a couple of us had the opportunity to participate in Python coding with a drone and having it fly around a room, which was kind of cool, which is very cool, teaching us how to code in the context of a drone, which is just a lot of fun.
And it
So
really adds to Curtis being in his cockpit there.
it does. It's very appropriate, isn't it? Yes. We don't know what he's doing there, what he's flying. So let's suppose that the height of the drone, a drone, in feet is modeled by this function capital H. It looks horrible there, but I guess it's really just a rational function. It's the quotient of 2 polynomials. So T is measured in hours from, what is it, 12 p.m., so from high noon. So this drone has a pretty good battery. It's actually in the air for 6 hours, okay? So the very first thing here is we need to be able to sketch a graph of this function, capital H. This is just a good technology tip. It's a good technology skill. How do you make sure that you can sketch a graph of a function over its domain, making sure that you have all of the important features? So I did a little bit with the X and the Y axis here, okay, rather the T and the H axis, so that I could see sort of the important features of this graph. My graph goes a little bit to the left of 0, and I did that so that I could get in a vertical axis there, so that I make that a little bit more visible. It just gives me a little bit more perspective, and I recognize that the height of this drone is not less than 0, but you'll see that I brought that horizontal axis up just a little bit also, again, giving me a little bit better perspective on this graph. So there it is. And Tom will show you how to do that on the 84. I basically defined this function on the TI-Nspire on a calculator screen, and I called it H, and then went to a graph screen and set the window parameters X min, X max, so that I got a nice graph like this. Well, let's work with this function H a little bit. The first thing is, can we find the times at which the drone was 300 feet above the ground? Well, on the Nspire and on the TI-84, there are a couple of different ways to do this. I'm going to show you a couple of ways on the Nspire, and Tom will have some techniques on the 84. On the Nspire, remember that I have this function called H already defined here. And there's a built-in function on the Nspire called zeros. And so what I'm really doing here is asking the calculator to find out when is that function, hey, the pen is working again, when h of t minus 300 is 0. I am solving that equation. setting it equal to 0 and solving. And although it may be a little difficult to see, there is a vertical bar in there right after that parentheses, which I read as a such that, or given that. So it's saying to the calculator, find the zeros of this function with respect to t, such t is between 0 and 6. Now, it came back with 3 values, and notice that these 3 values are in a list, and that's one of the reasons that I like to use zeros. So that I've actually assigned a variable to this list. And I like to do that because now I can refer to any one of those values individually, like z sub 1 or z sub 2. Z sub 3 would give me the 3rd value in that list. And remember, they're printed with 3 digits to the right of the decimal, but of course stored much more accurately. That is one way to do it. There are built-in functions in the calculator to help you solve an equation like that, where h of t is equal to 300. Another way to do that is on the graph screen. And so I don't know if you can see this in color, Curtis, but my graph of h here is in blue, and I drew in a horizontal line here at 300, and that's in green. And what I really want to do is find out, where do those two graphs intersect? Well, there's a built-in function on the 84, on the Nspire, that will allow me to find out numerically where those two graphs intersect. So I actually did that 3 times, and I actually left the point, or printed the point, on the curve, or on this graph, excuse me, on this graph screen. There's the t equal to 0.2. Let's see, there's the t equal to 0.953, and there's the t equal to 4.597. So look, technology tips for exam success. One of the things you need to be able to do is to graph a function, make sure you see all the important features. And another thing you may have to do is to solve a function equal to a value. And this is a way to do it with the command, built-in command zeros, or on the graph screen. There's more here. Let's see, another thing that we do in AP Precalculus is we talk about, search for maximum values. So it seems to me, as I look at that graph of h, it's kind of hard to see, but this is a tick mark right there that corresponds to 1. There's a 2 and a 3 and a 4. Whoops, I'm sorry, a 4 over there. And it sure looks to me like there is a maximum value of h in between 0 and 1. So let's see if we can find it. Couple of ways to do that. On a graph screen, there's actually a built-in command that says, hey, let's find the maximum value of that function in an interval. And so I set a lower bound, I set an upper bound, and it came back, and be careful here. This is the t value, but that's actually the maximum value right there, 420 point, what is it, 234. So a little over 420 feet in the air. That's one way to do it. Another way to do it numerically is on a calculator screen on the 84, the Nspire. The Nspire has a built-in function called NF max. Correct me, Curtis, here if I'm wrong, a numerical function max. So I'm going to find the maximum of that function numerically, h of t. I'm going to find the maximum with respect to t in between 0 and 1. And there it is, it's 0.472. Now remember, I have my calculator set to 3 digits to the right of the decimal, and I know what's coming here, so I want to store that value. I want to store it to the greatest degree of accuracy possible, and so what I did is I simply hit the answer or the store key, and I'm going to store that in a variable that I'll call a. And just to double check, the height at a is 420.234. Yep, that's that value over there. I'm feeling really good about this. Both the calculator screen and the graph screen seem to agree. I think I found the maximum height between 0 and 1. Vicki, I know you're going to remind me about this, but in these kinds of problems, if students are in fact asked to find the maximum height, they must report that 420.234, not the t-value of 0.472. And they have to be careful here not to report an ordered pair. because
Right.
of the report, right?
They need to be careful that they are answering the question. So they've got to carefully read what they're asked to do. Now, these are more likely to be in a multiple choice question, so it makes it a little bit easier. But
Yeah.
I'm sure there could easily be distractors. That means the three answers that are not correct that might, if you don't know which one you're supposed to talk about, the other one might be there in the list of four choices.
Might look appealing, yes.
Yes. Oh, look, I see a number on my calculator.
Yeah, there you go. All right. Well, let's do something similar here in part D. Let's find the minimum height of the drone for T between 1 and 3. Okay, here's again, here's 1 and 1, 2, 3. Here it is over here. I can see by looking at the graph that there is some minimum height that the drone attains between those two values. So again, on the graph screen, there's a built-in function to find a minimum between two values, excuse me. I did that. Once again, you can see the T value, and there's the minimum height, just a fuzz over 115 feet. And similarly, on the TI-Nspire, there is a function called NFmin, numerical function minimum. There's my function, there's the variable, there's the interval 1 to 3. There's the value of T, 2.304. Is that the same? Yep, it is. I'm feeling pretty good about this. And once again, since I know what's coming here in part E, I'm going to store that value of T much more precisely. I'm going to store it in a variable that I'll call B. And this is just a double check. I want to evaluate my function H, remember, which I defined way in the beginning, just to make sure. And I did get that same 115.009. Everything seems to agree here. This looks really good. Now, let's put all of this together in part E. This is, I think, Vicky, is a typical sort of a question, like find the time at which it hits its maximum height, find the time at which it reaches its minimum height, and find the difference between those two values. That would be a really cool multiple choice question. I found the difference between those two values. It's 1.832, and I think we were in hours. And that might be a neat question that you would see on the multiple choice portion of the exam. So
Yeah,
notice to do that. I'm sorry, go ahead, Vic.
No, go ahead. Finish, and I
Well,
want you to scroll up in a minute.
I was just going to say that when you take this difference, make sure that you do indeed use these variables B and A that I created and then I stored these values. You don't just want to read off 2.304 and type that in and whatever the value was for A and type that in and subtract. Because of rounding, it is quite possible that you will get an answer that would be incorrect in the third decimal place. So you should definitely use the most accurate value stored by the calculator. Go ahead, Vic, sorry.
So no, I was going to ask you to scroll back up to the one where you had the green horizontal, like y equals 300.
Yeah.
Okay. Where is? Oh, was it not this one? It was the other one.
Here it is, right here on the
Oh,
left.
there it is. Yes.
Yeah.
Okay. So there has been a question. I mean, it is very much related to the one that you just showed us, but it's like what's the time interval from, and there were only 2 points of intersection, not 3
Yeah.
like we have here, but what's the time interval between the 2 times that it was at 300 feet? Like how long? And so it's the exact same principle of what you just showed, but they've got to realize they need to use the stored values and that they've got to subtract, and they're subtracting those T values for how long.
Gotcha. And another typical question would be, what's the difference between the maximum height and the minimum height?
Yeah.
Right?
Yes.
Okay. Tom, sorry, we got a lot for you to do on the 84. Sorry about that.
All right.
Okay, there you go.
All right. All right, I'll pull up the 84 again. I think it's up okay. And yeah, let's dive right into it. So on 84, we could go and use the y equals menu. The independent variable for y equals is x. So we'll just use x in place of t in this particular case. And we've got a rational function. So I'll go ahead and pull up a fraction template here and enter my numerator and denominator of my rational function. So we've got 8 times...
I think it was 800, Tom.
Oh, sorry. That would make a difference.
Just a slight one.
Just a little bit.
So 8 times, let's see what we got, 3x cubed.
Yes, sir.
And come down, minus 12 squared, 12x squared. And again, x is playing the role of time for us here.
Yes.
Yep.
And then plus 17, and again, x in place of t. So there's our numerator, and we'll move down to the denominator, and we've got 14 x squared plus the square root of 2. And I'm going to have to hit the right arrow key to get out from under that square root sign.
And that is something students make mistakes in doing. And I think
Easy
you
one.
putting them, yeah, and seeing that multiplication, I think emphasizes it, makes it more clear whether they really do or don't have it out from under the radical sign.
Yeah, and that's why I put that times in there, is just to make sure I was okay. And so I think,
and it's also,
go ahead,
I think you did. No, it's really important in a function like this that you use that fraction template and not try to do embedded parentheses here. It's just, it's so easy to make a mistake when you try to use the embedded parentheses to separate your numerator and denominator. So make it as easy as possible on yourself as either a teacher or a student.
Yeah, that's a good point, especially for these rational functions like that. I think if we can do the visual check with what we're trying to enter so easily. Okay. All right. So let's go ahead and graph this. And I think we've got a particular domain here. So I'm just going to go ahead and jump to the window right away and put in 0 and 6 for my x min and x max, because that was the t interval that we're interested in. And then I'm going to go now to the zoom menu. And I'm going to scroll all the way down past all of these to zoom fit. So what that'll do is it'll take my x domain from x min to x max and actually kind of samples what would be a good y range, what would be a good y min and y max to use to fit the graph on. So let's try that and see what we get.
But only use zoom fit when you have a set domain. And typically that's going to be in a problem that is associated to some context.
Yes. Yeah. And of course, I mean, otherwise you'd have to kind of sample some values by hand and try to pick, or do it by trial and error until you got a reasonable picture. But zoom fit is nice when we've got a restricted domain. Yes. Okay, so this looks great. And then we could do similar things to what Steve did. We could add a horizontal line at 300. Graph again. Great. There we go. It looks like there's 3 places. We're interested in finding a particular place. We can go to our calculate menu. And number 5, intersection. Looks good. First curve is the blue one. Okay. Second curve's the red one. Not many other choices. And then I guess, now I'm arrowing over, but you could enter a value close to a guess. But I'm going to just go over close to this first intersection point. And when I'm pretty close to just eyeballing it, I'll hit enter, and then it homes in on it. Okay, and there I see that x value. Now here's just a reminder, and I found, Steve mentioned we were at the TQ conference. I think this is something people might not have been aware of, is that x value and y, that intersection point that we just calculated, that x and y value are actually stored in x and y for the time being. So you wanted to save that value of x, you could quit off the graph screen and just type in x. And there it is. There's the x value for that intersection. So we could store it away if we're going to need it later on. I'm not going to store this one away, but Steve's had some later parts to his question where he needed a couple of values that he calculated and needed to take the difference. So I'll use it in that case. All right, so let's go back to our graph. And let's see. Steve said he wanted a maximum in the interval from 0 to 1. So let's go back to our calculate screen. And by the way, I only calculated one of those three intersection points. We could calculate the other two just as easily. So let me choose number 4 for maximum. And we're on Y1. Okay, so left bound. Well, he said it was from 0 to 1. So I'm going to actually go to 0. That's my left bound. And then my right bound is 1. So I'm actually entering the 2 endpoints of that interval that we wanted to use. And then the guess, well, I'll just go kind of eyeball approximately. It'll be about halfway through there. And there's the maximum at that X value of 0.471733. Now, we actually want to look at the difference in that time. That's a time value, and the time where it hits this minimum over here. So I do want to store that value of X away. So let me quit off the graph screen, pull up the X. There it is. And let's store that in A. Okay, now it's safely stored away. We can go back to the graph and this time calculate a minimum. And our left bound, this was between 1 and 3. So let me enter a left bound of 1 and a right bound of 3. And I'm just going to type in 2 for my guess, kind of halfway in between. And it homes in on the minimum there. That's that 2.303. So let me go quit. Excuse me, what did I do there? Let me quit. Okay. And pull up that X value. Okay. Now I got that X value right there. I'm just going to subtract off A. And there's our time difference between those.
How about that? Very cool.
Very nice. But this storing values that you calculate off the graph screen, being able to store those away, that's a fantastic convenience. It for one thing, it saves that step where you can make a mistake is if you're copying it down on paper and then re-entering it. It cuts out the middleman, and there's all kinds of opportunities for mistakes there. This is also giving us, it's maintaining precision. So, if we did intermediate rounding, there's always sometimes a danger there when you start doing a lot of calculations with numbers that have been rounded beforehand. So.
Yeah, but just make sure students that are here, you start right after you calculate it. Don't wait, because then you might be storing the wrong thing that you did.
Well, and that's why I always call it up first and take a look at it and see, is that really the value that I wanted? So for example, if you accidentally traced a few pixels over after you calculate it, well, that's going to be the new X value at that point.
Right.
All right. I'll turn it back over to you, Steve, unless.
All right. Pretty cool.
Okay.
All right. One more to go here. Let's see what we can do with this one. Beautiful. Okay. I'm probably going to do some overkill stuff on technology here, Tom, but let's give this one a shot here. The domain of a function f consists of only 5 real numbers, 1 through 5, and the table defines the values of f for those values 1 through 5. So there's that table. There's a new function g, and it's given by this expression. So g is actually an exponential function. In the exponent, it might be a little difficult to see, but in the exponent is minus x divided by 8. There's a 0.5 out in front. So we have this new function, and it always seems like in the free response portion of the exam that there's a question about a composition. So I think the way that I write this, I think that students should understand that notation. This is part of notational fluency, and they should know that function h of x, the way that it's defined, means that's g of f of x. So the very first thing I want to do is simply find the value of h of 4 as a decimal approximation or indicate that it's not defined. So we're going to actually find this with our calculator, and we're actually going to do this 1.5 ways. So again, this is really overkill, but it turns out that you can define a piecewise function, a piecewise defined function, on the TI-Nspire, and you can also do this on the 84, although I think on the 84 there's a maximum of 5 pieces.
That's correct.
Is that correct? But this is kind of weird. You don't think of this as really a piecewise defined function because there aren't any inequalities in here. But I mean, there's no less than, there's no greater than symbols, but this is okay to do. You can actually define a function like this with 5 values. And then what I did is I defined this function g, this is my exponential function, and on the Nspire, I can actually define my composition. There it is. H is g of f of x. So if I want to evaluate h at the x value of 4, I can do that on a calculator screen. There it is. And there's my value to 3 digits to the right of the decimal. I think Vicky helped me on this, but classic multiple choice question, huh?
Oh, actually, it's a classic free
Free
response
response.
question
Okay.
1A.
1A, okay.
But yeah, it could easily be a multiple choice question. But I do want to remind students or teachers that
Yes.
inputting that f of x is a little bit time consuming. This is a really neat thing, especially if maybe you have a set of problems that keep referring to that table. But if
Yes.
it's a single problem that's referring to that table, I wouldn't do that much
Wouldn't
work.
take that time. Yep.
Yeah. And I am going to say that you and Steve's going to go through his written work down there, but you do have to show some intermediate steps now. This is new for this composition. You just can't write the answer down. So you need to show something similar to what Steve has down there, g of f of 4, is g of 10, and then evaluate it.
So without doing anything like this, here's what I would do, is I would convey how I am finding the value of this function h. I'm plugging in 4 first to the function f, and I get that value by looking at the table. F of 4 is 10, so I need to evaluate the function g at 10. There it is, and now I'm going to go to my calculator and simply evaluate that expression, and I hope indeed that I do get the 0.143. So I think, Vicky, if I understand correctly, you're going to have something like that
Yes.
paper in order to earn full credit.
Yeah. And this is new for this coming 2025 exam. The statement of show work was not there last year, and it will be there this year.
Okay, cool. All right, part B here. What does it say? Find all the values of x as a decimal approximation for which g of x is equal to 2, or indicate that there are no such values. This sounds like one of the questions on the FRQ too, doesn't it?
Yeah.
So we've already done something a little bit like this on the TI-Nspire. I can actually use the zeros function. And what I'm doing here is, again, I'm solving this expression, g of x is equal to 2, and I'm bringing the 2 to the other side. I'm getting all of the non-zero expressions on the left-hand side. I'm finding the zeros of that expression for x, and there's only one. It's a minus 11.090. Again, I used the zeros command. Tom, what's the other command on the Nspire? Is it solve or nsolve? Is that correct?
It's solve.
Solve, I think, would do it.
Yeah,
solve.
I mean, yeah, it depends on, well, yeah.
I'm gonna say you've got a CAS machine there, so you could use solve, but
You could use
nsolve
solve,
is
okay.
really just what
Okay.
you need, and the numeric solver would do a fine job.
Okay. Okay, and here's a graphical way to do that. Same thing. This line, which I think you can see is in green, that's the line, a horizontal line. Y is equal to 2. There's a graph of g of x, and I'm simply going to find that point of intersection. There's the x value, and there's the y value of 2 for both of those functions. Good. These seem to agree. I think I found the right value of x. I'm looking pretty good there. And one more thing here, or maybe 2 more little things here. Oh, maybe 3, I don't know. Determine the end behavior of g as x increases without bound. Let's see. What happens as x increases without bound? Well, I really took a look at this in 2 different ways. I actually graphed the value of g as x got bigger, actually, I guess between minus 10 and 100. And it's kind of hard to see, but it sure looks like it's getting closer and closer and closer to the horizontal or the y-axis. It's getting closer and closer to zero. To back that up, I got a list and spreadsheets page, and here's the input value, here's the output value, here's the value of x, here's the value of g of x. Notice my values over here, e to the minus 544. Man, that's a pretty darn small number, okay? And when I plugged in, what was that, 100,000, it came back with just a plain old zero. So I'm pretty convinced that as x increases without bound, as x goes to infinity, the value of g of x is going to zero. And Vicky, students do indeed have to be able to write end behavior with a limit statement that looks something like that.
Yes, and if you will scroll up just a little bit to show us the function again, just as a reminder.
Sure.
I hate making you go back and forth,
Right.
but I think this is important. Students should be very aware of the behavior of that function as x approaches either positive or negative infinity. It is part of their essential knowledge with exponential functions. So you are confirming it both graphically and with the table, something that they should know. But you know, when they're taking a high stakes test like this, maybe they need to look at something like the graph just to make sure I'm not misinterpreting this.
Yep. Good point. Good point. Okay, determine if f has an inverse function. I'm sorry about this. I'm going to sneak back here to the table again. Does f have an inverse function by looking at that table? Now, you may remember that if we had the graph of a curve, we could determine by looking at that curve if it passes the vertical line test. We don't have a graph here. We just have this table. So how do we know whether or not this is a function? Well, it turns out here, let's see, is it? What did I, pardon me, I gotta go back and what did I ask? Does f have an inverse function? That's what it was. It's a function. Does it have an inverse function? That's what I asked. How can you tell on that one? Curtis, one answer, your one chance. What do you
one
say?
chance to get something right on the last evening with 3 minutes to go.
What do you say?
So you would not have labeled this function f of x if f was not a function. However,
It
that
is a
does
function.
not mean-
It is a function. Go
that
ahead.
does not mean that this is an invert, has an inverse. And I
Correct.
can see right now that if I were to think about the function, the inverse values, if you will, I would see that I may have trouble around 7 because there are two inputs at that point that would have differing outputs. So
Yeah,
7
so
would be
one of the key
correlated to
things here
1
in order to have an
and
inverse
3.
function is the function must be 1 to 1. And
Mhm.
that means that no two distinct x values can be mapped or sent to the same y value or output value. And so here 1 and 3 are both sent to 7. And so therefore f does not have an inverse function. Very good, Curtis. Okay,
All right, well, I need to jump in real quick.
go
They
ahead.
cannot say it's not 1 to 1 and earn credit.
Correct.
They must be very specific as to what two ordered pairs or points or input outputs have this issue that causes it. And the word that we use, our vocabulary word in AP Precalculus, is that it's not invertible. So,
not invertible.
Yeah, if it's invertible, it's 1 to 1 and has an inverse. So this one's not.
This is not invertible.
That, in other words,
there are two y values for different x values,
or the same y value for two different x values, but they need to call those specific values out. Like, look, this one has a 7 as an output, and this one has a 7 as an output. And that's my problem as to why it can't be 1 to 1 or invertible.
It is invertible.
All right, Curtis, we've run up against the end of our time here. We do have another problem, which we will post a solution to tomorrow sometime. This one has a couple of questions about increasing and decreasing, and also about concavity, which are also asked about on the AP Precalculus exam. So we'll have a couple of questions and some answers that we'll post tomorrow. How about that?
That is correct. Well, we will post some answers. We will also make sure that if you want to, you can email me. I will send a certificate of professional development hours if you reach out to me at curtis@ti.com. That is a completely acceptable way to get some a certificate. So I'll put my email address here in the chat, put that in there. We do have a couple of questions, comments rather, about this not invertible.
Go ahead.
One said, Tony Record mentioned that we have a pair of sevens, which is maybe good for poker, but not for and then the question, if a function is invertible, do I still need to give specific coordinate examples?
They need to give some evidence of what they're seeing in the table, specific of what they're seeing in the table or graph that says why it is. Yes, they've got to reference.
Like the function is one to one, therefore it is invertible.
That's not going to be enough. They've got to be very
specific.
specific.
Have to say, I do not have any other values.
Each X value is mapped to a unique Y value, Vicky?
Yeah. Yes. But I know this is kind of something we talk about a lot when we're grading AP calculus. It can't sound like a definition.
Correct.
It's got to be specific to the problem they are presented in some way. So they've got a reference like in the table or something that gives us evidence that they are not just spouting out a definition.
Not just spouting a definition. So
yeah.
Something like in the table, we see no, I don't know, repeats of Y values with different X values. Therefore we can, okay.
Yeah. And it's real beneficial if they use the words input and output. Right. That's a very common vocabulary theme throughout the course.
Right, inputs and outputs.
Mm-hmm.
Well, that's good. That's
very
really good. Well, I appreciate the extra information. Thanks all for joining and asking questions. Again, we will post the solutions here. And put them in here in the description, along with a link to the student document is already in there. And I guess this is our last one for this year. So good luck out there on the AP exam here coming up in a few weeks. And we'll pick this up again here in the fall.
Terrific.
All right. Think.